All right, so cool. Right now we're on the last topic of this chapter. Okay. All right. Before we go further, let me review. This is from the first video of this chapter, the definition of acid and bases, right, by Bronsted and Lowry. Right. So Bronsted and Lowry looking at proton and say, hey, the acid is a proton donor and the base is a proton acceptor. All right. And now, in the same year, we got an American scientist, American chemist named Gilbert Lewis. Okay, so Dr. Lewis, hold on, he got a PhD from Harvard in 1912. Went to UC Berkeley for his tenure, professor there. All right, but now he looked at the acid-base reaction at the electron pair transfer, not a proton transfer like Bronsted and Lowry. Right, so he said base is an electron donor and an acid is an electron acceptor. Take a look right here. So what's happened in this reaction? So ammonia used a lone pair, attack proton of the hydrochloric acid, and the proton give up the electron, go up to chlorine. So 3 lone pair chlorine become 4 lone pairs. You know? And the lone pair of nitrogen disappear and become a bond between nitrogen and a proton. Okay, so Lewis look at an acid-base reaction at the electron. So the Lewis base and the electron donor, and the Lewis acid is the electron acceptor. That's what he said. Okay, all right. Before we go further, let's review. Let's concept check real quick. If you get what I say earlier. All right, who's the Lewis acid? Who's Lewis base? Looking at electrons, not a proton like a Bronsted and Lowry. Okay, actually, let me point out one thing real quick. I'm going to go back, sorry, real quick, right here. All right, no matter what definition you use, you can use Bronsted and Lowry, or you can use Lewis definition of acid and bases. Your answer should be the same thing. The base in Bronsted and Lowry, the same base with Lewis, you know, the acid in Bronsted in Lowry, still the same acid in Lewis definition. Okay, all right, so in this case, what happened? Looks like water gets the proton. See that? Which means that the oxygen gonna go attack proton of perchloric acid. Look like this. Ta-da! Yeah. According to Lewis definition of acid and bases, water is an electron donor. That's a Lewis base. Okay, and perchloric acid, that's is an electron acceptor. So that's a Lewis acid. Now down here, what's going on? Looks like water loses electron, and this guy ammonia gains a proton. Right? So ammonia attack the proton. This guy Lewis base for sure. All right. Now let's say what's going on. So a lone pair of the nitrogen donate to water. All right. And you're gonna have an electron donor, which is the Lewis base, and an electron acceptor, that's a Lewis acid. Lewis looks at an acid-base reaction this way, looking at electrons instead of proton like Bronsted and Lowry, because he wants to expand the definition of an acid and bases, not just in an acid-base reaction. I'll give you some example here. This is an example of not an acid-base reaction at all, right? But you can use Lewis definition to classify Lewis base and Lewis acid. All right. So water, use a lone pair, donate the lone pair to aluminum 3, form a complex. All right. So Lewis base here, Lewis acid there. All right. Try this one. This is not a Lewis an acid-base reaction, but you can use the definition of Lewis acid and bases to determine who's an acid, who's a base. Okay. It looks like ammonia go to form bond with a copper 2. All right. So ammonia will donate a lone pair to copper 2. That's a Lewis base and Lewis acid. Copper 2 is a Lewis acid, except the electron. All right. I stole this slide from Gen Chem 2. I'm not sure if you remember, in copper 2 is blue. The solution is blue, but copper 2 with the complex with ammonia, that's a dark blue. It changed the colors. Okay. All right. Last one here. So who's Lewis acid? Who's Lewis base? All right. Let's looking at what's going on here. So it looks like diethyl ether form bond with the boron trifluoride, right? So it goes this way. So an electron donor, that's a Lewis base, and electron acceptor, that's an acid. Okay. Down here, so we have carbon dioxide, we have sodium hydroxide. At the end, we have carbon dioxide attached to the hydroxide ion, right? So totally, this hydroxide ion, 3 lone pair go to 2 lone pair. Donate the electron for sure to the carbon dioxide, right? Donate an electron, Lewis base, and carbon dioxide accept the electron, so become Lewis acid. Okay, look like that. All right, last thing I want to point out, look at the boron real quick, okay? If you still remember the empty p orbital in carbocation, right? Carbocation, which is C plus, and it got an empty p orbital there. Boron and aluminum, group 3 element, has an empty p orbital, right? Why do I say that? Let's do this real quick. So can you count the number of electrons around boron? Determine if boron is octet. Is this boron octet? Nah, 1, 2, 3, 4, 5, 6. This boron totally not octet. This is an sp2 boron. Okay, and since it's not octet, because it got an empty p orbital there. Boron by itself is really reactive because it's empty orbital. All right. I usually call boron and aluminum as a neutral carbocation, right? Carbocation got charge, positive charge, and that's why it got empty p orbital. But boron and aluminum, it doesn't have charge, right? It's neutral, right? So, but it's a neutral carbocation because it got an empty p orbital there. And boron and aluminum, which have empty p orbital, is really reactive. Anything that have the lone pair can attack boron right there at a p orbital. Right. In this case, the diethyl ether attack boron at the empty p orbital there to form complex. All right. Okay. This is my last slide now. All right. Chapter 3, class activity 4. We have question 1, 2, 3, and question 4. Okay. The key is down here. All right. Complete it. Do it. Submit it on Blackboard. Quiz for this chapter will be due by Sunday night, so don't forget about it. I'll send an out email too. Okay. And that's pretty much it, guys. Thank you for listening to my podcast so far. Don't forget to subscribe, click like, and leave a comment if you like it. Tell your friends. Okay. All right. I'll see you for chapter 4 in a few days.